In this video, we will look at contribution technique and we'll also look at some problems that involve contribution technique, binary search, expected value, and counting the number of inversions in an array. So these kind of contribution technique problems are becoming increasingly more popular on Codeforces and AtCoder. But in order for you to assess whether this video is really for you or not, I'll quickly describe the problem statement, and if the solution sounds trivial to you, then you can skip this video. Otherwise, I believe you might have some learnings from this video. So the first problem says that you are given an array and there can be duplicate elements in this array. That's fine. It can have like 1 1 2 3 2 and so on, but you have to permute all the elements of this array. So how many ways you can permute? The number of ways that you can permute all the elements is n factorial. Why is it n factorial? Because we don't consider duplicates, because we are permuting the indices. So this is I1, this is I2, and I2 comma I1 is also valid permutation even though their values are same. So you already know that if you want to permute n numbers, there are n factorial ways in which you can permute them. So you have to do the permutation. So you started out with this array and there can be n factorial ways to shuffle it. So let's shuffle it in every unique way that is possible. So this is the first permutation. This is the first shuffling that you receive, second shuffling, this is the third shuffling, and so on. So in total you will get n factorial different arrays. So you have to count the number of inversions in this array, in this array, in this array, and so on, and you have to report their sum. So you have to print the number of inversions in all the n factorial permutations that you can create of this array. So this is the first problem. Now the second problem is that this time you are not permuting, this time you are not creating all the n factorial permutation. I say that if I take this array A and if I permute it randomly, you'll get some permutation of the indices. What is the expected number of inversions that I can find in this array that I just created by randomly shuffling all these elements? So this is the second problem that we will discuss. Then these are the easier version of the problem. Then there will also be a section for the harder version of this problem, where this time you are not given a single array, you have two array. This is array A and this is array B, and this time let us fix this array A and let's only permute the elements of array B. So again there are n factorial permutations, and once you have done the permutation, you create a new array where you define C of I is AI into BI. So notice that AI is not changing, but you are exploring all the n factorial permutations of the array B. So again, how many C arrays there can be? There can be n factorial C arrays, right? So this is the first C array that you can create. This is the second C array, and so on. So again, the problem is same, that you have to create all these arrays in n factorial ways. Then you have to count the number of inversions in each entry, in each array of C that you create, and then you have to report their sum. And then if you want to make it even harder, you can say something like, given this array A and given this array B, what if you randomly permute this array B? Then the array that you get, which is C of I, which is again defined by AI into BI, what is the expected number of inversions that you will get in this array C that you have created? So these are the different variations of the problem that we will discuss in this video. And there is no prerequisite, there is no probability or expected value prerequisite for this problem. At first glance, it might look like it, but we'll see how to solve these kind of expected value and probability related problems without using a lot of heavy concepts from probability, and in fact relying on combinatorics and number theory and contribution techniques to solve these problems. Now in this version, so this final version is the one that appeared in the Codeforces round, and we'll see how we can approach this problem starting from brute force whose complexity would be n square into n factorial. Then we'll optimize it to n to the power 4 using contribution technique. Then we will apply contribution technique again, and then we'll optimize it to n cube log n. And then we apply contribution technique once again, and finally optimize it to n square log n. So there will be a lot of layers of hidden contribution techniques that you will see in this video. So make sure to watch the video at your own pace, because I believe it would be a long video. But make sure that you are writing down things on paper, thinking out things for yourself as well, not just watching the video for pleasure, because this kind of format is a bit different from the other videos that I have on my channel, because in this video I'm planning to do a bit deep dive. So if you are just watching leisurely, then you might not grasp all the concepts. Anyway, with all that said, let's jump into the problem. So first of all, for people who are not familiar, let's see how do you find out the number of inversions and what are inversions and how to actually find them. What are inversions? How to count inversions. So first we discuss this algorithm. So let's take this array. So if this array had been sorted, if this array was sorted, then if you select any index I, and I is to the left hand side, and you select an index j to the right hand side, what can you say about AI and AJ? So you will see that if it is sorted, then I is less than j, it means AI has to be less than or equal to AJ. But what if this is not true? Like, consider this condition: AI is strictly greater than A of j. Then you can realize that this element and this element, they are misplaced. They are not in their correct position in the array according to their sorted version. Why? Because in the sorted version, a smaller element, see, this is the smaller element. So a smaller element should have appeared before the bigger element. But if this is not true, then we say that these elements or these indices, they contribute to an inversion. So they form an inversion pair. They form an inversion. So again, just to summarize, how do you find out the like how when do you say that two when do you say that two indices or basically a pair of indices creates an inversion? You say that when the left side element is bigger, because ideally in an ideal world, when the array is sorted, you want this to be small and you want this to be big. But if the opposite is happening, it means that these two elements are inverted with respect to the sorted order. So if you have this scenario, big appears on the left hand side and small appears on the right hand side, then this is an inversion in the array. So how do you compute the number of inversions? Let's look at a very simple algorithm to do that. We want to find out how to compute the number of inversions. So how can we do this? So you can see that all you have to check is that for every pair, because every pair can be inverted. So there are O of n square pairs in the array I and j. So for every pair you check whether the left element of the pair is bigger than the right element or not. So the algorithm would look something like this. You would have something like for I in 0 to n minus 1. Let's say let's say 0 based indexing, and for j in 0 to I minus 1, and then you check if ai is greater than aj, you increment your inversion count. So using this simple code you can find out all the inversions. Now you will see, now this is one important point that you have to keep in mind. So you see that I iterated I from 0 to n minus 1. So I could be anything, but j can only be till 0 till I minus 1. And this is an important point, because if you are considering I comma j, then I has to be less than j. Why? Because then you would end up over counting, double counting. Why? Because if you consider this element 3 over here, and suppose this element is 1, then these two elements are inverted. So suppose this index is 3 and this is 6. So you say that 3 comma 6 is inverted. So you say that this element is inverted with this, but when you look at things from this element's perspective, this is element 1, so this is also inverted with this. So in order to not double count, we have to avoid double counting. So in order to not double count, you can have a rule for yourself that says that an element, this is the element that you are considering, this can only be inverted to an element on its left hand side. So if this is the element that you are looking for, so you don't say that this element and this element are inverted, even though it is possible that this is 3 and this is 1. You don't say that this 3 is inverted with 1. In fact, you say the other way around. You say that this 1 is inverted with 3, so that you don't end up over counting. So we'll write that down as a rule. And this can actually be very helpful in inversion related problems, or in more general in contribution technique related problems, that you have to define some ordering between the elements. So let's define some ordering which says that element ai can only be inverted with an element to its left hand side. Now if you have been following my brain gym series video, if you remember, there was in episode 4 I believe, we talked about some greedy algorithms, and there we had utilized this concept of defining a strict ordering between these elements so that they do not get double counted. And then we saw in that video like how adding this artificial restriction helps us visualize things in a better way. And there is another reason for adding this restriction, because if you say that this element, suppose this element is j, if you want it to be inverted two elements on the right hand side as well as on the left hand side, this makes things very complex, because you are being inverted with the elements you have not even seen. So the standard data structures and algorithms that you have in your toolbox, that might generally not apply over here. But once you have this restriction, then you can see that for this element, it can only be inverted with the elements that you have seen so far. And then you can keep them in a particular data structure to find out count of certain set of elements that you need. So with that said, let's look at this code. So the time complexity of this code is O of n square, right? Because we are iterating every pair. Now, it is actually possible to optimize it to O of n log n using divide and conquer. In fact, if you know about merge sort, if you know how merge sort works, whenever merge sort is introduced, this is always added as a follow-up, because you can count the number of inversions while doing a merge sort. So this is a very interesting application that you might have seen in your algorithms class if you have taken one. But nonetheless, right now, divide and conquer and the merge sort approach is not that relevant to this problem. So I'll skip that part of this video. And if you are interested, you can also solve it with Fenwick tree, or you can use some policy based data structures for finding out the number of inversions. So you want to optimize this time complexity from O of n square to O of n log n. But again, this Fenwick tree optimization and the PVDS optimization are out of the scope of this video, so I'll not dive deep into that. For this video, you don't need any prerequisites. If you know how to count inversions in just O of n square, you are good to follow the rest of this video. Now notice that what we have just done over here is some form of contribution technique. Why? Because what we wanted to find in this array how many inversions are there, and then we said that you flip the narrative and you instead ask, if I consider any pair I comma j, will it contribute to an inversion or will it not contribute to an inversion? So this if and the increment that you are seeing, you can actually club them into one, and let's define an indicator variable that takes in I comma j, and it responds with 1 if ai is greater than aj. It means j is inverted with I, and it returns 0 if ai is less than or equal to aj. So you can see that this for loop, you can actually remove this part and you can simply add this for loop, and then you can do something like inversion count plus equals to the indicator variable of this pair that you have just chosen. So in other words, you can see that each pair I comma j is contributing something. And what is it contributing? It is either contributing 1 if the pair is actually inverted, else it is contributing 0. So this means that this is already the simplest version of contribution technique that you can encounter. So now, the next time you see an inversion related problems, instead of trying to find the inversions for an array, you can instead focus your approach on any pair of the array, any pair of indices of the array, which is I comma j, and ask yourself this question: is this element a of j, is it inverted with its neighbor, left neighbor, or the element on the left hand side, which is a of I? If yes, you add 1 to your answer. If no, you add 0 to your answer. And if you do this for all pairs, then at the end you will have your answer. Now This part is actually important to discuss. So why do you claim that if you do this indicator variable strategy for I as well as j, why do you claim that you will have all inversions? Because remember this term, you are doing an exhaustive search, because it is actually true both the ways. So if I comma j, if they are inverted, then they will contribute to inversion count of the final array. But you also have to check this other way around, like have you missed any pair? Because you can see that we haven't missed any case, because if two elements are inverted, then they would be counted in some I comma j for sure. And even though this might look very trivial over here, this observation that things need to be exhaustive, in a lot of problem this is not very apparent. Because if you remember my last video on contribution technique, the title of this video was that unexpected twist to a contribution technique problem. There we saw that it was not at all clear why something was exhaustive and why just iterating over the feasibility and not worrying about the rank led us to the optimal solution. So after this video, you can even try to watch that video that also has good concepts on contribution technique. Okay, so now with that out of the way, we have solved the first problem, which is how to count the number of inversions, and now we want to find out how to find the sum of inversions across all the permutations of A. So let's tackle that problem. So suppose this is the array A that you want to deal with, and let me write down the heading. Inversion count across all permutations. So we apply, first of all, we try to do it in a brute force manner. And how can you do it in a brute force manner? So if you have this array, then you can see that you can split it into multiple permutations like so. So you have split it into multiple permutations, and what will be the number of such arrays that you create? That will be n factorial. Now what is your strategy? You want to count the number of inversions in this using your O of n square algorithm, and then you want to repeat this for all the remaining arrays as well. So right now all these problems are independent in a way, because you are trying to solve them independently. You want to find out the inversion count of this, and then sum it up. But then notice one thing, that in this array, when you are applying your algorithm, when you know that you will apply the algorithm by trying to take the contribution from every possible pair that exists in the array. So you can say that counting inversions from this array is equivalent to counting the inversions contributed by each pair, right? Contributed by each pair. So you count the uh, inversion count of each pair. Now what we'll do is we'll try to make all of these problems coupled, so they won't be independent anymore. And we'll do that by saying that if elements, so when you are running your algorithm on this array, you will consider whether pair I and j are inverted or not, and you will apply that indicator variable. Suppose this is the I1 indicator variable that you apply to the first array, and the final, so the answer to this problem would be summation of all the indicator variable, right, for I comma j. And if it is summation of all of them, And the answer to the original problem is the sum of all the answers that you get from each array. Then you can notice that when you apply the same algorithm on this array, even then you would try to consider whether pair I comma j are they inverted or not. So you will again apply your indicator variable strategy. You will do I2 comma I comma j to figure out if I and j are actually inverted in this permutation. Then you will apply your same strategy over here, and you have a indicator variable of I comma j, but for this permutation. And now notice that this term will appear in the inversion count of 1, and there will be other terms as well, sure. This term will appear in inversion count of 2. Same, this will appear in IC3. And the problem actually asks you to find IC1 plus IC2 plus IC3 and so on. So then you can notice that this pair I comma j, it not just contributes to the inversion count of its own array. You can flip the narrative and you can say that any pair I comma j will contribute something to the final answer. And what is the final answer? The final answer is your inversion count across all n factorial permutation, right? You want to count inversions across n factorial permutations. So now we can say that each I comma j contributes something. Previously, so you see that this contribution technique is growing. Previously, it just contributed to one single array's inversion count. Now it is contributing to the sum of inversion count across all the permutations. So let's formalize that. So we can say something like each pair contributes something to final inversion count. And now notice another important fact, that if you are considering the pair I comma j, the indicator variable that you just defined, that only looks at what? AI and AJ. That only looks at AI and AJ. This means that when you are counting the inversions for this permutation, whatever you have placed here does not matter. Whatever you have placed here does not matter. Only thing that matters is, did you place a smaller element than me or did you place a bigger element than me? Then if you apply that same reasoning to this same index but in the other permutation, this same reasoning follows, that whatever you have placed in other location does not matter. I only care about what have you placed here and what have you placed here. So let's try to, so since these quantities do not matter, let's try to evaluate what can you actually place at I and what can you actually place at j and how many times. So to do that, let me take this. So this is your array and the index that we are dealing with, this is I and this is j, and we want to find the contribution of this same index across all the permutation. This is I and this is j. So what can go in at this location? Because inversions, keep in mind that inversions are always defined by the rightmost element of the pair. Defined by rightmost element. So you always say that AJ is inverted with AI. You never say that AI is inverted with AJ. So this is the convention that we agreed upon, that an element can only be inverted by the right, uh, by its left element, not by an element on the right hand side. So if it is defined by the rightmost element, then okay, let's consider this rightmost element. So what could land over here? So when you are shuffling, anything could land over here. So what are the possibilities? So either you could have a of 0 at that location, you could have a of 1 at that location, you could have a of 2 at that location, and so on. So there are n different possibilities at that location. So why don't we try out all of these possibilities? So you fix this a of j. And how do you fix this? You do something like this. You try all possibilities. So you can write something like for I, or you do something like for x in A, right? You place x at, in fact, let's use the indices. That would be easier. So if you want to figure out what you want to place over here, so you can do something like for j is equal to, sorry, just have to get the notations right, otherwise it will get confusing later on. So if you're trying to iterate over this I and j, so okay, let's go with this interpretation only. So you have fixed a0, you have fixed a of 1, you have fixed a of 2, and so on. Now what can be present at this ith location? Again, it could be anything except the index that you just fixed over here. So I at index I, what could be available? It could be either a of 0, or it could be a of 1, it could be a of 2, and so on. Then in how many cases will it be inverted, and in which cases it will not be inverted? So you can see that it will only be inverted if the element that you placed at the ith location, if this a of I is greater than a of j. And when it will not, so in all of these cases it will contribute 1. But when would it contribute 0? That would be the case where it is less than or equal to 0. But notice that we don't actually have to count how many times it contributes 0, because if it contributes 0, it contributes nothing. So all you have to do is find out how many times can you place one element over here and one element over here, and we actually don't care about what you placed at other locations, right? So how many times you can place one element here and one element here, so that this left element is big and the right element is small. So how can you do that? So what are the possible choices that you have? So let's explore the possible choices that we have for making it an inversion. So if this is the pair I comma j that you are considering, then at this location, at the ith location, you could have a of x, and at this location you could have a of y, and you just have to ensure that x is not equal to y, because you cannot place that same index at two locations at the same time. So you can actually try out all y from 1 to n, 1 based indexing. And for each y, because first you always fix the right element of the pair, for each y you fix all x from 1 to n, and then x should not be equal to y. And once you have fixed x and y, then you want to plant a of x at this location, and you want to plant a of y at this location. So if you have already fixed these two elements, you know whether they are an inversion or not. But then you also have to find out in how many arrays will, so you have just placed x over here. So this is a of x and this is a of y. But in how many arrays will this same situation happen? Because it's not just one array, there could be multiple arrays, right? So how do you find out how many times will this pair contribute? Because we want to find out this contribution of I comma j not from a single array but from across all this column, like this vertical column that you see, we want to find the contribution of it across that column. So how many times will that happen? So you see that you have just fixed two elements from the array, right, by iterating through them, and you actually don't care about what goes on these elements. But once you have fixed the values at index I and index j, how many elements do you have remaining? N minus 2, and you can permute them in any order that you wish, and in all of those n minus 2 factorial, this element at I would be a of x and this element at j would be a of y, and they would contribute to an inversion depending upon what the indicator variable says for ax and ay. So this means that the contribution of this pair I comma j to the final answer is n minus 2 factorial into this indicator variable that will decide whether x and y were they inverted or not. So if they were inverted, you add 1, so you replace it with 1, but if they were not inverted, then you don't care. So once you have added this indicator variable, you can see that you are fixing the values of the pair, you are fixing this I and j, and you are trying to permute the remaining element, and now you can visualize that there will be exactly n minus 2 factorial in which ax will appear at position I and ay will appear at position j, and in each of them they will contribute an inversion depending upon what their indicator variable says. So you can see that with just this simple observation you have solved the problem, because now you have counted the contribution for any fixed pair I comma j, right? But now notice that, like, what is the time complexity of this algorithm that we just discussed? Because it is not actually O of n square, it's more than that. Why? Because this y and x, this is not I and j. This y and x, we were deciding what to place at this location I and this location j. So you have just counted the inversion for any given pair I comma j, right? Any given pair I and j. But there could be O of n square such pairs, right? So you have to run this thing for all the O of n square slots for the indices, because each of them will contribute to an inversion independently. So for example, if this I and j is contributing, but if this element is p, then p comma j will also contribute. So your algorithm is something like, so the final algorithm is something like, for I in, first you iterate over j, because in all inversion related problem the rightmost pair gets the priority. So for j in, let's say 1 to n, and for I in 1 to j, and opening bracket over here so that we don't include it. And once we have fixed position I and position j, we want to count how many inversions contribution will come from this pair. But you have just fixed the indices, you have not fixed the values. So what value do you want to place first? Of course, at the right pair, rightmost element of the pair. So you do something like, for y in 1 to n, so any element can land over there. And what do you want to place and on the left element of the pair? you can place anything. So you add for x in 1 to n except y, and how much will they contribute? So this I and j that you have just fixed, they will have x and y as their value in n minus 2 factorial permutations, and then you add 1 if a of x is greater than a of y. Otherwise you add nothing, because the pair, fixing it the other way around, it will not contribute to any inversion. So the time complexity of this algorithm is O of n to the power 4. Now let's look at how to optimize this time complexity. But before we do that, notice that we are defining the contribution as I comma j, right? This is the contribution of a pair. But if you wanted, you could have another layer of contribution technique, where this time you say that I don't actually care about how much each pair contributes, right? If you want to actually find out how much this index contribute, because the most standard format in dp that you must have seen is something like dp of j denotes some contribution of j. So can we have some similar dp definition for the contribution technique of this jth index? So you know that in any permutation, the rightmost element is the one that defines the permutation. So you could have something like dp of j means how many contributions, how many times, how many times index j contributes, index j contributes to the inversion as the right element of the pair. Index j contributes to the inversion as the RHS of the pair. So that is the right hand side of the pair. So if I tell you, can you find out how many times this contributes? So this time you see that I actually don't care about what happens with I. I just want to focus on for each index how much this index will contribute. So this is a bit different, you will see, because this time we are saying that we are adding a contribution of a particular index, but then one index cannot be inverted by on its own, right? So in fact what we are adding, the contribution that we are adding is how many I comma j exist for a fixed j such that this I comma j is an inversion. So how do you find out this dp of j for each j? So you can do that by looking at this fact. So you have just fixed this j, but if you don't need I anymore, but even in that case I could have been anything from this or this one. So all these values contribute together with j. So this sum that you are getting, you can simply do something like this: dp of j plus equals to this. And once you are done with this iteration, you'll notice that dp of j contains exactly how many times this index j contributed as the right side of the pair. Now, not that it changes anything, but having the compression of the contribution technique just based on a single index might be helpful in future problems. It will not be helpful right now, right here, because we can only optimize it to like by a factor of n here. But in future, like if you want to optimize an O of n square algorithm down to O of n, you cannot take contribution from I comma j. Why? Because I comma j itself is a pair and you cannot iterate over all the pairs. So this means that you have to compress your contribution technique and then define the contribution technique on the right side of the pair so that you can take contribution directly without actually iterating over all the possibilities of the left hand side. So that was just a small tangent. Now back to the main track. So we have an O of n to the power 4 algorithm. That's fine. Can we optimize it? So in the n to the power 4 algorithm, notice what we wanted to find. So we had a loop for I. Sorry, we had the loop starting with j. We had the loop for j, we had the loop for I, we had the loop for x, and we had the loop for y, and we were checking if a of x is greater than a of y. Now let's try to optimize the time complexity. Right now it is n to the power 4. We can go as low as n square into log n, and you'll see how to do it step by step by trimming down some unnecessary for loops that we have. So the last for loop that you see, what is it actually doing? And actually, let me write it in the correct order that we have, right? I always say that you should keep the right element of the pair first. You have to iterate that first, and that's why you fix the right element of the pair, and then you fix the left element of the pair, and then you do the comparison. Now let's see if we can apply some more contribution technique inside of it. Right, like one example of a contribution technique inside a contribution technique is fixing the right endpoint of a pair and wondering how much this contributes to. So this has actual contribution technique embedded inside of it. Why? Because there could be multiple multiple i's for which the j is same, and it is actually storing the sum of all of these uh, pairs, right? Contribution from these pairs. So contribution of contribution. So that is why I had introduced that notation, because we'll apply that same technique over here. Now let's look at this element, what is happening over here. So you have fixed I, you have fixed j, and you have fixed the element at this location, and you are calling it as a of y. You have fixed the element at this location, and you are calling it as a of y. And then you are iterating over all the possibilities, right, in the original array. And this time notice that you don't care about ordering, you don't care about left or right, because since the elements would be shuffled, you want to place anything and everything over here. This is index I. But if you want to do that, can you not do the iteration manually and figure out how much this element, how much this index y would contribute if you give it this slot at index j? So how do you find the contribution of this index being assigned to this element j over here if you fix it over here? So this means that if you want to fix a of y over here, without iterating, can you actually find out how much this element will actually contribute? Because if you have this array, then you will apply this formula to every element of the array, right? You will apply this formula to every element except maybe x not equal to y case, x equal to y case. So you will not apply that formula to them. But other than that, you will apply it to every element of the original array, and you'll see how many times this condition is satisfied. But what does this condition actually mean? It means that this is fixed, right? Because we are finding the contribution when you give the jth slot to the yth index. How much contribution can it bring without even talking about this x? Because if you want the contribution from this y, then you have to take the contribution from everything and then add it up. So this is contribution technique inside contribution technique. So how much can this actually bring? So notice that this element is fixed, a of y is fixed. Let's call this as a key. So you see that you are looking for all the x in the array that are strictly greater than the key. This means, and you don't actually care about the ordering. So if you sort this array A, if you sort this array, and then let's say you have element 2, 5, 9, 22 and 30, and suppose this key value is 6, it means that you don't actually have to manually iterate over each, this element as x, this element as x, this element as x, and try it. Because if you sort the array, then you can try to do it manually, but this check would fail because this is less than key is 6. This check will also fail, but this check would pass. But this would also pass, this would also pass. So you will see that there is a pattern: fail, 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 and pass, 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 right? So there will be a suffix of fails, and then prefix of fails, and then suffix of passes. This means that you could just do a binary search for this key, and the total number of elements that are greater than the key. This is a very standard binary search problem. You can do that and you will find out the total number of elements that are greater than the key, and you simply add that count to your answer, and in this manner you can actually get rid of this x iteration altogether. So it would become something like, you have the iteration, you have the iteration for j, you have the iteration for I, you have the iteration for x, for y, and then this time you don't actually iterate x, but you directly add how much will this slot contribute if you give it. So this would simply be dp of j, because we wanted to find out how much this index j will contribute to the overall inversion count. So you can say dp of j plus equals to, for each y you are looking at count of ai, count of, like, let's say I should say a star greater than y, right? And you can get this count using standard C++ functions, which is called upper bound. So this binary search idea that we just discussed, you don't actually have to implement it, it is already implemented for you. So whenever you have a series of false followed by a series of true, then upper bound can give you how many times t appears in this array in log n. So now you can see that we have optimized the complexity to from O of n to the power 4 by to O of n cube log n by taking the contribution from this loop iteration y, fixing this y, and taking the contribution all at once via binary search, right? So let me also write that down. So we used binary search to take the entire contribution at once instead of iterating over it manually. So okay, so far so good. But then how do you optimize it down to O of n square log n? Can you actually remove this y factor as well? Now this is where things get a little interesting, because if you have been following the video so far, a lot of this might have looked like very trivial, because you have been familiar with contribution technique before. But this part, this optimization is not easy to see. Like this time, so previously I asked you to find the contribution of j and add it in, store it in dpj. So to find the contribution, you try to guess what could be the possible I, and then you try to guess what could be the possible y, and then you try to guess what could be the possible x, and then you added something to your dp value, right? You added dp of j plus equal to something, and then you said that okay, you don't actually have to iterate over x if you store the contribution directly into this y. But now the big question is, can you get rid of this loop as well? So can you find out the contribution of this jth index when this element act as the right hand side of the pair? Can you find out this contribution without actually iterating over what you can possibly place over here? So how do you do this? How do you actually get rid of this y for loop? Because it at right now it looks very impossible. So actually there is a way to get rid of this and then find out the contribution of this j directly, even like without iterating over either x or y. So let me show you how. So let's see what we are actually doing. So we are fixing this j as a of 0, and then we are fixing it as a of 1, and then we are fixing it as a of 2, and then for each value that you fixed, you are doing a binary search to find the number of elements that are greater than this. For this, similarly for this element, you are finding the number of elements that are greater than this. But then this choice, this itself is n choices, so you cannot afford to do n iterations. So so far we have trying to so far we have been trying to find the contribution by fixing some I and fixing some j. But let's look at it from a holistic point of view, like what happens when you want to find out the contribution of this index I and this index j. So what can go over here? A of x could go over here, and what could go over here, that is y. So if you can just find out how many times you can create ax and ay such that ax is greater than ay and x not equal to y, that simply is your contribution of all the y's combined. So this time we are not looking for the contribution of a single y. We are just saying that I directly want to find out the contribution of this index. But the contribution of this index can only come from when you placed ax over here and you placed a of y over here. So there are n square ways to place, there are n square possible values that you can have at this I and jth location, ax and ay. So in how many ways, in in how many of these O of n square pairs is one of the elements greater than the other element? Because if that is the case, then we can take that as here and take this over here. So how do you do this? So we try to simply mimic what we want to do, right? We want to consider all the pairs, and we want to place this time we want to place the pairs together. Previously what we are doing is, the reason why our time complexity was increasing, because we are fixing this and then we were iterating this. But then we said that, okay, I don't want to iterate this, I don't want to fix this as anything, I just want to fix this. But this time I want to say I don't even want to fix this. But if you could, then there could be only O of n square choices to place, right? So let's try to find out what all the choices could be. So you create an array with you create an array of pairs. You do something like a of 0, a of you have a of 0, a of 1. This is one element of your pair that can be a candidate. And then a of 2, this is one element that could be a candidate. This is another element that could be a candidate, and so on, right? Now there can only be O of n square candidates, right? So suppose you have iterated through all the O of n square candidates, and every time one of the element of the pair, basically the first element, every time you saw this scenario, ax is greater than ay, you keep track of how many times have you seen such a scenario. So suppose you have seen 50 times, like you have created all the n into n minus 1 by 2 pairings, and 50 times you saw that the first element of the pair is strictly greater than the second element of the pair. Then you can see that even without explicitly iterating over x and y, you can see that in all those 50 pairs, this this index I and j, they will contribute 1, in the remaining they will contribute 0. So if you do this pre-computation, right, if you do this pre-computation, that is, for each pair you compute all the pairs, and then for each pair you find out how many pairs is the first element strictly greater than the second element. And if that count is c, then the contribution of dp of j would be simply dp of j plus equal to c, where c is the number of pairs in which the first element of the pair is strictly greater than the second element of the pair. So this, in this manner, you see that you completely eliminated x as well as y from the picture, and you took the contribution directly. Now you will see that there is another contribution technique hidden behind it. What is that contribution technique? Because when you saw this count variable, who is actually contributing to this count variable? All your pairs x comma y, right? Because even though you remove the y loop from here, you remove the x loop from here, when you created these O of n square pairs, when you created this O of n square pairs, then each time you are simply counting how many times this pair will contribute as an inversion if you give this slot to index x and if you give this slot to index y. So just by doing this pre-computation and figuring out what is the, because this count will not change regardless of what is this j, what is this I, the number of pairs that exist in the array such that the first element of the pair is greater than the second element of the pair, this is fixed, right? This you can find out. In fact, you can, now you might ask me, why am I creating O of n square for finding this out when you could apply some binary search and fancy tricks to find out this count even faster? So to that I say that it does not matter, because the time complexity will be dominated by this O of n square loop that you see over here. So you might as well create all the pairs by hand manually, and then you count simply in how many pairs. So if there is pair x1 and y1, and here you see that a of x1 is greater than a of y1, so you see, you say that this pair contributes to the count of pairs, in which count of pairs that can actually be placed at this location I comma j. And if there are 50 pairs, then placing these 50 pairs will result in an inversion, and placing all the other n square minus 50 pairs, they will not result in an inversion. So this means that the number of times this element j contributes, right, which is dp of j, that is nothing but dp of j plus equals to count. And in this manner we have solved the problem in O of n square. So see, we started from n to the power 4, and now we are down to O of n square. So first we started with n to the power 4, then we went to n cube log n, and then we finally went to O of n square. So in O of n square, not only were you able to find out the number of inversions in a single array, but you could also find out what is the sum of inversions across all the permutation of the given array A. Now let's quickly talk about expected value. So if I take this array A and if I permute it randomly, what is the expected value of the number of inversions? You will see a lot of problems talking about this concept of expected value of the number of inversions. So how do you find out? Like, you only have at your disposal the sum of inversions across all these, right? But how do you incorporate probability and expected value into this? So in these kind of problems, even though the problem mentions expected value, you will realize that it's not okay to actually skip this problem, because previously I also used to skip a lot of probability and expected value problem, thinking that I don't have that solid base for probability or expected value. But later you will realize that if you are good at DP and contribution technique, then you can solve almost any expected value problem. And the only fact that you will have to use is this thing. So if you want to find out the expected value of x, so you try out all the possibilities. So you say that it will be, so what is the probability of this happening into what is the expected value when this has happened. So what I mean to say is, this is expected value of x is nothing but summation of probability of s happening. So s is a scenario into what is the value when x has happened. Now I'm not going into very formal definitions. Here I'm focusing on how we can use the expected value concepts in competitive programming. So for expected value, we say that if you want to find out the expected value of the number of inversions across all the permutations, so you say that what is the probability of getting a particular permutation, and then what is the probability of a particular scenario happen, into what is the actual value, because once that scenario has happened, you have a permutation that is fixed. Once that has happened, what is the inversion count when that thing has actually happened. So how can you apply this technique over here? So you will see that if you want to find out the number of inversions across all the permutation, then what is the probability that your permutation is this one? The probability is simply 1 upon n factorial. What is the probability that the permutation is this one? It is simply 1 upon n factorial. What is the probability that the permutation is this one? It is simply 1 upon n factorial. But then we said that what is the probability that this scenario happens, and then once this scenario happens, what is the number of inversions in this array. But now notice that it's very difficult to find the number of inversions in this array, because the contribution technique has added the sum of all the things. But if you want to ask for a single array, I cannot find out, right? Then I'll have to do this experiment for each array. But luckily for us, I said that there is also a summation term in the expected value. So there is a summation of a scenario happening. So you can remember this formula. So expected value of x is equal to probability of a scenario happening, and then value of x when this scenario has happened. And then summation of this. So we don't know the number of inversions in this. But if you sum it all up, then what will you get? You can take 1 upon n factorial as common, and you are looking at summation of the inversion count in in any particular permutation pi. And this technique we know how to solve. So this is the big idea behind expected value. So you don't bring probability into the picture at all. You find out the number of ways to do a certain thing, and then you simply divide it, because probability of permutation being picked is 1 upon n factorial, and then you have to sum it up across all the permutation. And then that is the problem that we just discussed, like how to compute the number of inversions across all permutations of way. So this part we already know how to do with contribution technique. It means that the answer of this problem that looks very complicated, what is the expected number of inversions when you permute A, this is nothing but the answer to this problem divided by n factorial. As simple as that. So now let's talk about this hard version of this problem. And this time you are not given the array A, you are only given the array, sorry, this time you are not only given array A, you are given two arrays A and B, and this time you are not allowed to permute A is fixed, but you can only permute B, and there will be n factorial permutations, and you have to find out in how many permutations, like once you have permuted B, you compute this array Ci as Ai into Bi, and you find out how many inversions there are in Ci, and then you sum it all up. So once you sum it all up, you also have to find out what is the expected value of inversion count that I can expect if I shuffle this array randomly. So let's see how to do this. So this is your array A, this is your array B. So again, we can apply the same strategy, and we want to first of all find out how to get the number of permutations, sorry, number of inversions across all the permutations of B. So we can apply the same contribution technique. We ask the question, in all of these permutation, how much will the pair I comma j contribute? So I comma j could be anything. We have to iterate over all the pairs. So we iterate, of course, we iterate j first. We iterate j, then we iterate I. Now ai and aj are fixed. Notice that ai and aj are fixed, right? And you can, ai and aj are fixed, but what you place over here at this location, bi and bj, they are not fixed. So if you are permuting all the elements, what element should go over here, what index should go over here, and what index should go over here. So again, you have a loop for y, and then you have a loop for x, and then you can summarize that you place b of x at I and b of y at j, and then you simply add the contribution because if you have already placed bx and by, you just check whether the array that gets created. So what is the array that will get created in all of these cases? And remember that we don't actually care about all the elements that are not part of the pair. So we only care about ci and cj. So what would ci be? So ci would be ai into, what did you place at the ith location? You placed b of x, and it would be c of j would be a of j into b of y. So once you have placed it, if you see this formula that cj is greater than ci, you simply add it as an inversion, right? But in how many subarrays will it contribute? So you see that this formula does not depend on any other elements that are not part of this pair. So again, you have n minus 2 factorial ways to permute the remaining elements. So you add n minus 2 factorial if ci is greater than cj. So this already gives us O of n to the power 4 time complexity, and we have solved the problem in O of n to the power 4. So let's also quickly look at the code while we are doing this. So first we defined dp of j is the number of inversions that is contributed when j is the second element of the pair. So you define your dp so that this time when you are counting the contribution, you actually want to count it for the right side element of the pair. So actually in this problem it doesn't matter a lot, but since I have a habit of taking the contribution from a single element only, instead of taking it from a pair. That's why I have defined dp of j, so that finally I can print the sum of dp of j as the answer. So the code is simple. You iterate over all the j, then you iterate over all the I, then you iterate over what do you want to place at j first, right? Which is the y that we have been talking about in this video. And then you decide what do you want to place at I, which is the x that we have been talking in the video. And of course, you cannot place the same index over there, right? Then you create your ci, which will be ai into bi, and your so you create cj, which would be a of j into b of y. And then if this is an inversion, it will be an inversion in n minus 2 factorials, in n minus 2 factorial different permutations, right? So you add this, so this dp of j, so dp of j, it means how many permutations does j contribute as the right element of the pair. So you see that there are n minus 2 factorial permutations in which j acts as the right element with an inversion with I. So, and how do you find the answer? So the answer is the sum of dp of I. Why is it so? Because every inversion that gets created, we need to get an exhaustive set, right? So for each j, if you find the number of inversions that this index j contributes by acting as the right pair, then if you sum it up over all the array elements, then you would have taken all the possible pairs, because the right pair has to exist in this array only. So this is n to the power 4. Now again, how do we optimize it? So to optimize it, we'll try to remove the loops one by one. So let's see how we can remove the for loops. So we'll start with this j, this I, this y, and this x. First, let's see if we can remove this x for loop. Now, if you want to remove this x for loop, let's see what are the things that are constant. So you want to, let's see what value we are utilizing this for. So when you are fixing things, right, you are fixing a of x, sorry, you are fixing b of, so this is the location I and this is the location j, and you are fixing b of y over here, and you want to ask the question, is ci greater than cj? So ci would be nothing but this LHS, which is ai, which is fixed, mind you, because this j and I, they are fixed, right? And b of I would be equal to b of x, and we want this to be greater than by. So we want this to be greater than cj, right? So this is a of j into b of y. Now notice that this is fixed, right? Let's notice what is fixed. This is fixed, this is also fixed, and since you are iterating y first, this is also fixed. It means that you are looking for, in the array b, you are looking for all the elements that are greater than this quantity. And what is this quantity? That is nothing but aj into by upon a of I. So the quantity on the right hand side is fixed, and you want to find out how many elements are strictly greater than this. Again, we can use the contribution technique that we discussed. We can sort the array, and you will see that it will have a pattern of false, 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 followed by true, true, true. So you just have to find the upper bound of this key, and the total number of elements that are greater. You actually don't have to place each and every x, you can directly count, and that will be the contribution of this y. So you can remove this inner for loop and use the contribution of this y, that location that you have added, and the time complexity already improves from n to the power 4 to n cube log n. So let's quickly look at the code for that, the optimization that we just discussed. So you see that you have the same, you fix the right element of the pair, you fix the left element of the pair, then you fix what you want to place at the right element, and then you don't actually fix what you want to place at the left element, you just count the contribution via binary search. So you see that this is the numerator that you wanted, aj into b of y, this is the denominator and this is your key, and you are looking for all the elements that are strictly greater than key, right? And of course, if you are doing the binary search on the array, you have to make sure that this key, this doesn't become equal to this element that you have just chosen, right? So that's why if you have over counted, you like reduce the count by 1. So okay, this is good. Now we have optimized the time complexity to n cube log n. But now coming back to the code forces problem, and in fact, if that is what you came for in this video, now we'll talk about the same optimization technique on how to optimize it from n cube log n to n square log n. Again, if you have followed the previous parts correctly, then you actually don't need to watch this part. You should come up with this optimization on your own. How can we optimize it? So remember, our goal this time is to get rid of this loop that fixes the value y, right? We don't even want to fix the right element of the pair. So how can we do that? So you have this array A. So this array A is always fixed, that's fine. And at B, you want to decide what you want to keep so that you can create this C array and then count the inversions. So if this is your I that you're dealing with, this is your J that you're dealing with, and this time we are saying that I want to get rid of this for loop of placing something at index J. So how can I do this? So at this location, so right now we have been thinking very narrow minded, because we have been thinking, okay, if I fix something, what can be over here? But what if you don't fix anything and you ask the question at once, like how many pairs, right? We ask this question because now we are trying to apply the contribution technique from the pair. So there is another level of contribution technique over here, just like we discussed in the previous videos, in the previous section of this video. So we want to ask this question: how many pairs contribute to dp of j? But how many pairs there can actually be? So there are only O of n square pairs, and these pairs can be created beforehand. So you can create an array of O of n square pairs, right? And the first element uh, of the pair will act as x and second element will act as y, and you only store the indices, right? But this time, notice that previously we said that each pair, whether or not it would contribute, that was already decided based on whether the first element of the pair is greater than the second element of the pair. But this time it's not that simple, because you need to have this entire pair, and then you need to figure out if you are placing, like let's say ax over here, and you are placing ax over here, and you are placing a of y over here, then that pair will only contribute to the inversion if the ci that it creates, what is the ci that it creates? This is actually bx and by. So the ci that it creates, that would be what? A of I into b of x. This is the first element of the pair, and this should be greater than a of j into b of y. So can we actually try to see which pairs will contribute without actually iterating over all the pairs? So now you have to apply some observation skills, and this part is not actually uh, obvious, but if you have been following some some of my brain gym videos, you will see that these kind of observation skills are very much needed in competitive programming, that you try to rearrange some things. So you see that you have this AI and AJ, right? You see which terms are fixed and which are not. So this AI is fixed and AJ is fixed. So you do something like this: AI and AJ is greater than B of Y upon B of X. Now, what do you conclude from here? So you see that this is, yeah, so this is AI into BX and this is AJ into BY, right? And you want to find out, so you bring this AJ over here, and let's flip this equation around. Uh, so if you look at it from the perspective of this second element, right, which is the second element of the pair, that would be AJ upon AI, right? And this left hand side you will have B of X on top, and then you will have B of Y, and this would be less than or equal to sign. Sorry, this will actually be a greater than sign, since you like reverse the elements. But either way, like regardless of whether you do this refactoring or not, notice that what are we looking for? We are looking for all the pairs where the ratio of the first element to the second element is greater than the ratio that we have at our hands right now. So this means that every pair, only for a particular pair, what matters is the ratio of the first element to the second element, right? So if you define this, if you define something like this, you first of all you create all the O of n square pairs and you store it in an array, and then you create another uh, array called ratio, and in that array, for each pair x and y, you store x by y, right? So you will have n square entries over here. You store x1 by y1, you store x2 by y2, not actually x by y, but it's actually b of x1 by y1 and this one. So once you have all the ratios, now notice that if you call this as your key, if this is your key, then what do you want to find? You want to find in this ratio array how many ratios are actually greater than a key. And again, how can you do that? Because since there are only n square possible ratios, because pair can come from I and j, and I could be n and this could be n, then you can brute force through all the pairs and store it in an array and then store it in a sorted order. But how do you sort these pairs? You sort it by the ratio. So if you keep the ratios sorted of all the pairs, then if you look for the key, suppose key appears over here, then all the pairs that had the ratio higher than the key, they will be on the right hand side. So you can find it via binary search how many elements are strictly greater than this ratio. And this count is nothing but because every pair, that is every ratio greater than this ratio, originated from a pair, right, x comma y. So you see that this ratio contains contribution from the pairs, and this ratio will now contribute to dp of j. So this means that all you have to do is find out how many pairs are strictly greater than this. Now, and if you do that via binary search, you should be able to solve the problem. Only the last hurdle is that notice that ax upon ay is not really an integer, right? This ratio is not an integer, right? This is not an integer, and this is also not an integer. So if it is not an integer, then doing binary search on doubles and long doubles is very risky, because you will have a lot of precision errors and whatnot. Because see, because if AI is if AI is, like, let's say 5, then this will directly convert to 0, which is not good, right? Because this cross multiplication can still yield some useful result, but division, even though division, if you really want to store it, you can store it as decimals, that's fine. But then decimals binary search won't really be very accurate. So what you need right now is a way to handle ratios, like a data structure to handle ratios. But that is actually very easy to implement. So you implement basically a function or a struct, and this struct, you don't actually divide it. You store what is your numerator and what is your denominator. And when you want to sort two elements, and you how do you sort two elements based on their ratio? Like, whoever has the smaller ratio should come first. So to sort this, if you want to find out whether a by b is greater than c by d, you don't actually do by division. You don't actually do the division. You just check whether the cross multiplication is valid. If it is valid, then this element of the pair is greater. So if you just maintain a data structure for these fractions and ratios, then you can do the binary search as we discussed, and then you can completely get rid of that for loop. This j and I for loop will remain, but y and x, this you can completely get rid of. And then finally, if I also asked you to print the expected value of the number of permutation of the expected value of the number of inversions if I permute B randomly. Again, same strategy. There are n factorial ways. So expected value would simply be 1 upon n factorial into sum of permutations, sum of inversions across all permutation, which is exactly the value that we found over here. And in this manner, we have solved the problem in O of n square into log n. So let's quickly look at the code. So first you write a class for managing your fractions. So you have numerator and denominator. And when do you say that this LHS is smaller than RHS? So you just do the cross multiplication and check if it is actually smaller. And then you can sort the array B. So B will actually not be needed. So this B was from the previous iteration. But now you have to just create the fractions, right? And fractions can be O of n square. Remember that we wanted the pairs to contribute to DPJ, right? So we iterate over all the pairs and we create all the possible pairs at I comma j, and we store their numerator as well as denominator, and then we sort these fractions based on their ratio. And once we have sorted them, we fix the right element of the pair that we are counting for inversion, fix the left element, and count the contribution directly without fixing bi or bj. So this is a very cool trick that you'll see. Like, this is actually a bit hard to grasp, like if you're looking at it for the first time, like how you are iterating over all the possibilities without fixing anything. But this is something that will require some time. Like, you have to spend some time with it, think through it, and eventually one day you'll get it. And once you do, you'll never forget this technique. And yeah, once you get the count, the dp of j, basically the contribution of the element as the right element of the pair, is n minus 2 factorial into count. And in this manner, like yeah, we have discussed all the problems in this video. And I hope like you got to learn something new from this, if you did actually stick around to the end of this video. Make sure to solve this problem, because it teaches you a lot about fractions and modular arithmetic, contribution technique, binary search, ratios, and whatnot. So make sure to solve this problem. I don't think it's a difficult problem at all. Like even though it deals with expected value, if you really understood contribution technique, then you could have solved this problem. But even if you don't, I hope that you got to learn something new from this video. So if you have any feedback for me on this kind of long form content, do let me know in the comment section. Because so see, one thing that I would agree, even before reading any of your comments, is that things were a bit slow paced or things were repetitive. But I'm trying to work on those, but I cannot do a lot in that area, because when you are creating a video in one go, so it's actually not possible to get that feedback of whether you are repeating things so or not. So this is different from a classroom setting. So I think one major problem with online education that I see is that in a classroom setting you can actually see the faces of all the children, and when you're teaching something, they can actually, from their expression, you can figure out if you're repeating things or not. But when I'm on this whiteboard and I'm just speaking to a mic, I don't actually have an idea of like how much ground I already covered, which part I'm taking very slow, which difficult part I am skipping. So these kind of problems are there, sure. But of course, like as and when you mention your feedback in the comment section, maybe I'll try to take some of those feedback and try to incorporate it. And yeah, another thing that I was discussing is that the length of these videos would be long, because since these are not planned, right? And these are not planned videos, and I don't know which audience is familiar with which technique, right? So I have to cover most of these in details, and due to this there could be cases where towards the end of this video I'm uh, rushing towards things and then not covering the difficult parts. So if you see that happening, do point it out in the comment sections, and I will link down the problem in the YouTube description. Make sure to solve it. Thank you.